Okay, so you might have heard the term "le mou," maybe on shows like Le Podcast de Philippe.
It sounds a bit sci-fi, right? Robots made of squishy stuff.
Yeah, it really does. But it's a very real and rapidly growing field. We're talking about soft robotics.
Exactly. And for this deep dive, we've gathered insights from, well, quite a few sources, expert analyses, research papers, to really understand what these flexible machines are all about.
Our goal is basically to get you up to speed on why they're so different and why there's so much buzz around them.
So let's start there. What actually is soft robotics? How is it different from, the robots we usually picture?
Well, the core idea is moving away from rigid metal and plastic. Soft robotics uses materials that are inherently flexible, elastic, deformable. Think silicone, rubber, plastics, even gels and polymers.
Right, less like a car assembly robot and more, more organic.
Precisely. There's a huge inspiration from biology, especially invertebrates, octopuses, worms, that sort of thing. It's not just mechanics and electronics. Material science is really central. And that shift in materials unlocks new abilities, doesn't it?
Absolutely, like handling very fragile objects without crushing them, or moving through complex, sensitive environments. Imagine a robot navigating inside the human body for surgery. That's a key area.
Okay, that's already pretty mind-bending. But I read something even wilder: robots moving without computers.
Ah, yes. That's fascinating work, like the research from the Amolf Institute. They've shown robots can move just based on how air flows through channels in their flexible bodies.
No software, no sensors.
Essentially, no central brain telling every part what to do. The movement and coordination emerge from the physical design, the material properties, and how different parts are mechanically linked, kind of like how our muscles coordinate.
Wow, so the intelligence is sort of embedded in the material itself.
In a way, yes. It's about mechanical coupling, not computation. And this can lead to surprising efficiency, too.
Efficiency? How so?
Well, think about that manta ray-inspired robot. It uses these clever, bistable wings that can snap between two positions to swim faster, and it does this without a motor pushing it. It's all in the wing design interacting with the water.
That's ingenious, and the innovations don't stop there, right? What about self-repair?
Another really exciting area, some of the elastomers, these rubber-like polymers they use, can actually mend themselves if damaged.
You mean like if you cut it, it fuses back together?
Yeah, often with a bit of heat. They've done successful tests with soft actuators, the parts that make robots move that can self-heal. Imagine robots that can just patch themselves up after wear and tear.
That would be incredible for longevity.
Yeah.
So with all these unique abilities, flexibility, gentle touch, self-healing, maybe even brainless movement, where could we actually see these robots being used?
The potential applications are really broad. Healthcare is a big one, as we mentioned, for less invasive procedures. Industry, too, handling delicate goods, working in unpredictable environments where a rigid robot might fail or cause damage.
What about exploration?
Definitely. Navigating confined spaces like pipes or rubble, or maybe even exploring other planets, the materials can be cheaper and potentially more robust for space missions.
Okay, and I think I saw mentions of agriculture. Logistics?
Yeah, gentle interaction with crops or livestock, autonomous drones for delivery, even things like wearable haptic devices. Imagine feeling virtual objects more realistically because the device touching you is soft.
The range is huge, but it can't all be smooth sailing.
What are the major hurdles? What challenges are researchers facing right now?
Oh, there are definitely challenges. For one, simply modeling and simulating how these soft, complex structures will behave is really difficult compared to rigid systems.
Because they bend and squish in unpredictable ways.
Exactly. Then you need to actually develop new soft materials with the right properties. And integrating sensors and circuits that can also stretch and bend along with the robot's body, that's a major engineering problem.
Flexible electronics integrated into soft bodies. Yeah, I can see how that's tough. And how do you make them do things reliably? That's the actuation challenge. Developing soft actuators, maybe using things like air pressure, special fluids, or even liquid metals. And then there's control, achieving complex tasks, coordinating movements, especially without a central computer, maybe enabling self-organization or more advanced self-healing.
It sounds like a whole new way of thinking about robotics, from materials to control.
It really is.
Yeah.
And it also means rethinking how humans interact with them, the command interfaces, especially for cobots designed to work alongside people safely. Plus, we need standardized ways to actually build them, which isn't like traditional manufacturing.
So how are they being built? You can't just bolt them together.
Right. 3D printing is becoming absolutely crucial. It allows for creating really complex shapes and, importantly, printing with multiple types of soft materials at once.
Multi-material printing.
Yeah, embedding sensors or actuators directly during the printing process. They're even integrating things like nanomaterials or magnetic particles to give the robots specific properties. There's work on tiny 3D printed magnetic robots you could potentially steer inside the body.
Wow, miniature steerable robots. Okay. And you mentioned nature earlier. How significant is that biological inspiration?
Hugely significant. It's called biomimicry or bioinspiration. Scientists are constantly looking at how living things, plants, animals move, sense, and adapt, and trying to translate those principles into robotic design.
Learning from evolution solutions.
Precisely. Trying to capture not just the mechanics, but sometimes even the inherent intelligence of biological systems. There's research into creating robots that can learn and adapt in unknown environments, like maybe exploring a collapsed mine inspired by how animals navigate.
That's incredible. But with more capable, adaptable robots, do ethical questions come up?
They certainly do. As robots become more autonomous, especially soft robots that might work closely with humans or in unpredictable ways, questions about safety, responsibility, and control become really important. Public acceptance is another factor. People need to trust these machines.
That makes sense. Okay, looking forward then, what's on the horizon? Where is soft robotics headed next?
One major trend is the integration with artificial intelligence. Combining AI's learning and decision-making power with the physical adaptability of soft robots could be, well, transformative.
AI controlling soft bodies.
Yeah, think improved autonomy, agility, maybe even voice or gesture control becoming more intuitive. There's talk about large action models, kind of like ChatGPT, but for controlling physical actions being a big deal for robotics.
Interesting. Are we seeing specific examples of this AI integration yet?
We're starting to. Humanoid robots, sometimes with soft components, are being used as platforms to develop and test AI for physical tasks. Some are already doing simple manipulation jobs in industry.
What about the environmental side? Are soft robots potentially greener?
There's potential, yes. They could enable more targeted use of resources, say in agriculture. And there are efforts to make the robots themselves more sustainable, lighter materials, electric actuation instead of hydraulics, even research into biodegradable or organic materials for printing.
Biodegradable robots. That's a cool concept. Any other futuristic ideas emerging?
Well, there's talk of neuromorphic systems electronics designed to mimic the way biological brains and nervous systems work. Integrating these into soft robots could lead to much more sophisticated sensing, control, maybe even biocompatible prosthetics or advanced human-robot interfaces.
Wow, mimicking the nervous system.
And another fascinating concept is swarm robotics, but with a soft twist. Think link bots, simple robotic units that coordinate and achieve complex tasks, like moving over rough terrain or carrying objects together just through basic physical interactions, no central command needed.
Like ants building a bridge, almost.
Kind of, yeah. It points towards low-cost, resilient, energy-efficient robot systems for things like disaster relief or adaptable manufacturing. It brings us back to that idea of decentralized intelligence.
Okay, so to wrap up, we've seen soft robots leverage flexible materials for unique capabilities, moving in new ways, interacting gently, even potentially healing themselves. There's still big challenges, particularly around control, materials, and manufacturing.
But the progress is rapid, driven by things like 3D printing and bioinspiration. And the future looks towards integration with AI, more sustainable designs, and maybe even radically new forms of robotic intelligence and coordination.
Which leaves us with a final thought for you to ponder. What does it really mean if robots can effectively move, adapt, and even solve problems without a traditional centralized brain? How might that shift our whole perspective on automation and technology's relationship with the natural world?
It's definitely something to think about.
If this deep dive into soft robotics sparked your interest, you should definitely check out Le Podcast de Philippe for more discussions like this. And hey, if you enjoyed our exploration today, please consider subscribing. Helping us reach 1,000 subscribers allows us to keep bringing you these deep dives into really cutting-edge science and tech.